Hi, welcome to the Ashok channel Physics. This is another video on electric current. And previous classes we said about electric current, electric field, potential difference, drift velocity, resistance factors affecting resistance, and equivalent resistance when they are connected in series and parallel. And in the last one we said about cell construction. If you are having any doubts in the electric current, you can check the previous videos. And in order to support my journey, please subscribe the channel so that you will get the notifications whatever I am saying. Okay. So in the next classes, after completing electric current, we will discuss about electromagnetism. So we will clear the concepts in this channel. Okay. So without wasting time, just enter into the concept because that is very interested. Physics concepts are always interested than our words. Okay, so here we are entering into the concept again, which is the Kirchhoff laws. So here we are saying first Kirchhoff first law, which is also said to be the junction law, which is also said to be the current law. You can call with different names. This is also said to be a junction law or a current law. So the name suggests that you can apply this law when there is a junction. Okay, suppose if you are having a junction, at a junction, if so many in a circuit, at this junction, if so many conductors are connected, likewise, we are connecting so many conductors here. So if a current coming here, which is I1, if another current is coming here, which is I2, if another current is coming here, I3, and if it is I4, and if it is I5. Okay. So Kirchhoff junction law suggests that so there is no accumulation of the charges at a junction. Charges never accumulated at a junction. Whatever the charges that are flowing into the junction is equals to same number of charges will flow out of the junction. Current is a vector physics. Current is a scalar physical quantity, so that you can add them scalarly. That means you can add plus and minus. So the currents which are coming to the junction we are taking as a positive, and currents which are leaving from the junction we are taking a negative, and there is no accumulation of the charge is there. That means the current at a junction is zero. There is no accumulation of the charge is there. The current at a junction, if I take junction law, you can write the statement of junction law. The sum of currents, that means the algebraic sum of currents. Algebraic means you can consider the plus and minus. So currents which are coming towards the junction you need to take as positive, and if they are leaving from the junction you need to take as negative. But at a junction, if you take at a junction, if you are calculating at a junction, then the algebraic sum of currents at a junction is 0. There is no charges accumulated at a junction. At a junction, if you calculate, the algebraic sum of the currents at a junction is 0. There is no charge will accumulate. No charge will store here. Or you can write another statement here, as there is no another charge is stored. Any charge is not stored here. That means whatever the charges coming at a junction, the same number of charges leaving from the junction. Or you can write the statement, the sum of the currents entering at a junction, the sum of the currents entering at a junction is equal to sum of currents leaving from the junction then only there is no storage of charges. Leaving from junction. Either way you can write the statement. Okay. So the statement, this is the statement. If you apply mathematically, the sum of the, first I am applying that one, the algebraic sum of the currents at a junction is 0. Algebraic sum means, so towards the junction I am taking as positive, away from the junction or negative. Here I1 is coming towards the junction, I2 is coming towards the junction, I3 is coming towards the junction. But I4 is not coming towards the junction, it is moving away from the junction. I5 is also moving away from the junction. Then, if you consider all of them, currents coming towards the junction I am taking as positive. And currents leaving from the junction I am taking as negative. That is plus of I4 and minus I5 is equals to 0. So then you can write this one as I1 plus I2 plus I3 plus into minus is minus, minus I4 minus I5 is equals to 0. If you send these minuses to the right hand side, then it becomes I1 plus I2 plus I3 is equals to, if you send these two, becomes I4 plus I5. So the second statement is also verified. So here I1, I2, I3 are coming towards the junction plus, that means that the sum of the currents entering at the junction is equals to sum of the currents I4 and I5 are leaving, sum of the currents leaving from the junction. So this is the junction law. And here the question you are going to get here, on what basis junction law is stated? So junction law is stated on the basis of law of conservation of charges. There is no charge is created, no charge is destroyed. Whatever the charges that are coming, the same number of charges are leaving. There is no another charge is created and the charges are not destroyed, which is based on the law of conservation of the charge. This is about Kirchhoff's junction law. And next law is Kirchhoff voltage law, or it is also said with the loop law. Okay, is it clear the concept? A simple concept. Okay. And next Kirchhoff voltage law, or we can call that one as loop law, which is based on the law of conservation of the energy. Junction law is based on law of conservation of charge, and loop law is based on the law of conservation of energy. Kirchhoff's second law, which is said to be the voltage law or loop law. Voltage law or loop law. Okay. So the algebraic sum of the potential differences in a circuit is 0. That is the loop law. So the algebraic sum of potential differences. The algebraic sum of potential differences in a loop is 0. So this is the loop law. Suppose if you are having a loop like this, suppose if this is a battery which is having an internal resistance which is R1 and which is connected to a resistance, external resistance which is R, and there is another battery. This battery is having a EMF E1, this battery is having a EMF E2, this battery is also having an internal resistance which is R2 and is connected here. Okay. So in order to apply Kirchhoff loop law, you need to consider a loop. Suppose these points I am considering as this is point A, we are having a junctions A, this is another junction B. These are said to be the junction. This is not a junction. Here only a turning is there. Here a junction. So that means current can move in this direction or in this direction. Okay. So you are having two junctions. Okay. So between the two junctions you need to apply a loop. So I can apply a loop in this direction, or I can apply a loop in this direction. Between the junctions you need to apply the loop. Okay. So if I am applying a loop which is A, and we are moving towards E1 and R1, and we are coming here B, and we are coming through R and enter at A, then only loop completes. From where we have started, you need to end at that point, then that is said to be a loop. Here that is, it is one loop, and you can consider another loop. So you can take in this direction or you can take in this direction, either direction is possible. I am taking in this direction, another loop is A, I am moving towards E2 and R2 and B, and you need to end at A here. So then R, and you need to end at A. You can consider another loop, the total loop. That means you can move from A towards E1, R1, you can come to the B, and from B you can move through R2, and you can move through E2, and you can come here A. So this is also a loop. There are 3 loops are there. By considering the 3 loops, the algebraic sum of potential differences. So you need to take the potential difference. This is having a cell potential difference which is E1, and the potential difference across R1. You need to find out potential difference across R2 and potential difference across R1, R and R2. So by calculating the potential difference, if you add them in a loop, that becomes 0. Okay. Suppose that means you need to take the direction which is positive, and which potential difference you need to consider as positive, and which potential difference you need to consider as negative. So you need to know that one. Suppose I am trying to find out the potential difference across resistances. So if this resistance is R1, or anyway, suppose current here, this is moving from, current always moves from positively higher potential to positively lower potential. So here the current from I1 I am calculating as I1. That means the current here in R1 is moving in this direction. I1 is moving in this direction and enters at negative terminal. So, and here from this one, from E2, current moves from positively higher potential, which is I2, and enters at a negative terminal. So this is the direction of I2. Here at R2, I2 is moving in this direction. While coming here, these currents, I1 is entering at junction A, I2 is also entering at junction. The sum of the currents entering at junction is equals to sum of the currents leaving from junction. This is I1 plus I2. Current will move through R. Okay. So then, which potential difference? Here the potential difference across R1 is I1 R1. Potential difference across cell is E1, which is the EMF. So then, which direction you need to take as positive and which is negative? So here across R1, if you take the potential difference across R1. So here R1, for R1 this is at a lower potential. Okay, not for R1. So we will say generally, suppose if you are having a resistance here and it is at a higher potential, this is the direction of the current. So if the direction of the current is given in this direction, and this is point A and this one is point B, and current is given in this direction, and what is the direction of the current? Current always moves from positively higher potential to positively lower potential. So then if you calculate in this direction, calculation is done in this direction, then BA minus BB. So VA is at higher potential, VB is at lower potential, and I am also calculating in the same direction. Then potential difference is, this is at higher potential, higher minus lower, then you will get a positive. This is 5, this is 4, 5 minus 4 is 1, which is positive. Then you will get the potential difference, which is I into R, which is positive. Here it is positive. Suppose if I am calculating in the same direction and the current in a resistance is in the reverse direction, if a current is moving in this direction and my loop is in this direction, so this is point A and this is at point B. Now if I am calculating in this direction, that means VA minus VB. I am calculating in the same direction, which is VA minus VB. If you calculate, then here VA is at lower potential, current is moving from higher potential to lower potential. VA is at lower potential, VB is at higher potential. Then you will get this one is negative, which is minus I into R. So that means if your loop and your current, if they are in the same direction, then you can take that one as positive. If your loop and the current are coming in the opposite direction, then you can take that negative. You can take in the reverse direction also. That is also correct. So different teachers are different methods are calculating here. And next, EMF. This is the potential difference across E1. So as you are moving from plus to minus, that means if you are calculating in this direction, this is at higher potential and this is at lower potential, plus 2 minus, this is VA, and if it is VB, as you are moving from higher potential to lower potential, then this one is taken as a positive. So then VA minus VB, that means across the cell you can take this one as positive. So suppose if this is a cell and if you are calculating in this direction, then you can take a VA, this is a B point and this is A point. So then VA minus VB, I am calculating in the reverse direction, which is VA minus VB is equal, sorry, if you calculate in the same direction, but here the cell is in the opposite direction. Suppose if this is negative and this is positive, and this is at lower potential and this is at higher potential, lower minus higher, then you will get this is negative. You can calculate, you can take in the reverse also, that is also correct. Suppose if our loop direction and current direction are same, then you can take IR as negative, that is also correct. If your loop direction and current direction are opposite, then you can take this one as positive, that is also correct. So if this is moving from plus 2 minus, then you can take as negative, that is also correct. If you are moving from negative to positive, then you can take that one as positive, that is also correct. So anyhow, these are not the perfect rules. So you can take any direction, any rule is taken. Suppose if I am taking, I am applying this one for this loop, which is AER1BRA. So this is the loop I am considering. So first, when you are moving from A to E1, there is no potential difference is here. There is no equipment is there, so there is no potential difference. And I am moving from higher potential to lower potential. When you are moving from higher to lower, this is the direction. Higher to lower, then you need to take that EMF as positive. I am taking that EMF as positive, E1. And you are moving from E1 to R1. E1 to R1, this is the direction. Sorry, there is a small disturbance. Okay. So, as we are moving in this direction, and current here is across R1 is coming in the opposite direction. when you are moving in this direction and current is coming in the opposite direction, then potential difference is taken as negative. So that is minus, and current here is minus I1 into, and resistance is R1. Okay. And next, you are moving from R1 to B. R1 to B, there is no equipment is there, so there is no potential difference. Again, you are moving from B to R. You are moving opposite to the current. Then potential difference is, when you are moving opposite to the current, you are moving opposite to the current, then potential difference is a negative, which is minus, and current through R is minus I1 plus I2 into R. And coming to the A, this is the algebraic sum of potential differences in a circuit. Okay. So you can take in the reverse directions also. You can take this one as minus, this one as a positive, and this one as a positive. Either way is correct. So you can send to the right hand side. Again there becomes positive. Okay. So this is how we are applying Kirchhoff voltage law. So now we have completed the Kirchhoff current law and the Kirchhoff voltage law. Kirchhoff voltage law is based on the law of conservation of energy. So these rules are not perfect. You can take in the reverse direction also, whether if you move in this direction, if current is also moving in your direction, then you can take this one as negative. You can take in the reverse direction also. So this is about the Kirchhoff voltage law. In the next class, we are going to discuss about heating effects of electric current. When an electric current is moved towards a conductor or through a conductor, so then you will get a heat is developed across a conductor. So then how much of heat is developed by the conductor? So we are going to explain in the next class. Okay, thank you.